So for those who are not familiar, analog devices, or ADI to its friends, we work for Analog Devices. We're a semiconductor company, and one of the many things that we specialize in is in bringing data from bringing the physical world into digital data, and that means we collect data through sensors, we measure things, but then we also have the ability to connect that data to other systems, to process the data, and even manage power. I can very confidently say that whatever you have in your pocket in the form of a phone, we help the power go into it and manage it. So we're very, very prevalent, and we do a lot of cool small things. Big impact though. So one of the areas that we focus on, and we're moving deeper into that range, is the concept of physical AI. You probably heard of Edge AI, where the idea is that data is collected, processed, and responded to, acted on wherever things are actually happening. That's the concept of Edge AI, which is very powerful because a lot of devices or in a lot of situations, there's not enough time to go to the cloud and back for inference, or even go to a different room in some cases, or it needs to be very small. What we do these days and what we think about with physical AI is the notion that a lot of devices these days work off of algorithmic solutions. A lot of them mimic or work based on physical formula and physical information, and where we are now increasingly developing and diving deeper into is the world of translating those physical concepts into physical AI, where we take the algorithms or we take the formulas and convert them into neural networks, where everything is differentiable, and that allows us in turn to optimize more easily and come up with models that are much smarter. So a great example for this, and this story was in an IEEE presentation on Sunday, has to do with 5G. Who here loves 5G? Everybody. We love TikTok, we love it, having the ability to watch it wherever we are, mentionable, unmentionable places. But what we don't necessarily talk about a lot is the fact that 5G, to get the data so fast to all of us and have good signals and fast transfer speeds, we need to use a lot of energy to make that happen. And that's bad for our environment, and even worse for the mobile carriers, because they need to pay the electricity bills, and it's at the level where it's actually impacting their profitability. ADI loves big challenges, and this is a very big challenge. We also have opportunity to control some of it because we have one of our components, a power amplifier, is inside of many of these antennas and base stations. And what we did is take the very many mathematical formulas that are involved in tuning these devices. They even have cool names to those formulas, but then deconstruct them into physics-based elements that then become parts of a neural network. And the neural networks themselves are not huge, but they're very impactful. What we were able to do is more easily optimize the power consumption to increase efficiency, clean up the signal that goes out of the towers, and reduce the interference between carriers, which for carriers themselves, if you are interfering, you get a big fine as a result of that. So that's just one example of what we do with AI. As a company, we have so many products that are somewhere along the what we call the signal chain, or even in this case, the consumption chain. But on the very, very small scale, opposite of cellular antennas, are tiny robots. We were part of a project where we enabled the very low power, very slow, very reliable communication between tiny robots. robotic swarms. And that was just one aspect. But the other aspect is we also built an algorithm to run on these robots that allows us to update the models that are deployed in a very efficient fashion by just adjusting weights and other elements of the model instead of shipping multi-megabytes of data. Another area where slightly prosaic but very important is what you see in the middle. That board allows data from across a car. If you know anything about electrical engineering, a car is a veritable nightmare of interference of all sorts of things that move and magnets. That allows cars to collect data from many systems and bring them in a very nice and trustworthy fashion to the main computers that control everything from your entertainment to self-driving potentially. So you really want data to be nice and clean. On a very different extreme, our healthcare research teams are working on planting accelerometers inside of hospital beds in order to allow patients to sleep through the night instead of being woken up in the middle of their sleep, just to make sure that they're still good. These edge models, these physical AI models, naturally need to perform their inference very quickly on the spot. So if you have a hearing aid, you really don't want the Netflix effect of seeing the lips move and then hearing what's happening. In real life, it could be very jarring. But even in that tiny form factor, one of the areas that we're investing heavily into is the authenticity of data. We are now we now have a technology in place that ensures that the source of the data is our sensor, and the part that is processing the data knows that it's a verifiable fact. So we can ensure the security even on very short hauls like that, that the data comes from our devices with a high level of trustworthiness. What is funny and alarming at the same time is that hearing aids were hacked. So it's growing in importance. Despite all of that, we again need to make things work very fast. So like most of you, we generally train our models in the cloud. We start with oftentimes very large data sets. But when it comes to inference, we have to take into account many other constraints, everything from running on a small, relatively affordable chip, all the way to operating for decades without updates potentially, in extreme temperatures, and always consuming very low power in the process. And naturally, we're not going to have a nuclear power plant like the nice man from Meta was talking about. This is like small batteries. So what's involved in this process is taking models, oftentimes open source models, and working very hard to minify them. And Sheila, who has the actual fingers on the keyboard, will talk at length about that. But minifying those models to the point where they retain their efficacy, but at the same time comply also with the constraints that I mentioned. And I can tell you, if you've done it once, it's a hairy undertaking. So that's the undertaking. There's a lot of effort necessary from figuring out what are the components and what's the processing unit that's going to be there. It's a long process, and there's a lot of iterations that are involved going back and forth. And a big lesson for us had to do with the concept of co-development. If the hardware team does one thing and throws the hot potato to the software team that throws the potato to the AI team, and we're not in complete alignment, this can be long and painful. And at the same time, if we do the opposite and we do co-design, which takes a lot of learning about each other and what works and what doesn't, it works much nicer. Now, if there's one takeaway from my spiel, is that there's very little opportunity for undo when you are on a device on top of an antenna or on an electric generation windmill. You really want to hit things out of the ballpark the first time, or at least show that you tried really, really hard to do that. The reason I'm mentioning that is that we're very, very big believers in AI governance, which is very much where weights and biases comes strongly into the fore, because they allow us to do a lot of the things that responsible AI and governance best practices offer. Things from tracking the model lineage to all the iterations and permutations that we do to data sets, which we need to track, and ensuring that models can be reproduced downstream. And if you don't do that, I highly recommend you do. Another thing that we need to deal with at global scale is the fact that we oftentimes, when we produce these models, they need to comply with a lot of government regulations and industry standards, which means things like GDPR, but also, if you're in the automotive world, standards like ASPICE, which essentially tells that you need to prove that you had a process and not just pulled AI out of a hat. So Sheila is going to take over now, and she's going to take you from the words to the action. So how we use weights and biases and how we offer the governance.
So yeah, as Yuval said, he's kind of painted a picture of what we're trying to achieve at ADI with physical AI and getting models on the edge. And I'm going to talk more about how we use weights and biases to accelerate that work. So as Yuval mentioned earlier, a key challenge getting models on the edge is to shrink them down and make them small enough to fit on the target embedded platform. And we have a number of techniques that our team uses to do that, some of which may be familiar to folks in the audience. But to go through a few of those, one of them is quantization. So the idea here is to take the weights and activations of your model that may start as floating point numbers and to reduce the precision to lower bit integers. And then your model is smaller and can execute faster. And oftentimes you can do this without taking a hit to the performance, which is great. We also use techniques called neural architecture search, or NAS. And so here the idea is to provide these algorithms with your constraints. So you can tell it what performance metrics you want to hit, how many model parameters you may want to have, or also just like how many operations the network can do. And then you feed these into the NAS algorithm, and hopefully it can output a network that it's searching over the space of possible architectures, and hopefully it outputs one that meets your constraints. There's also knowledge distillation. Folks here may be familiar with this, but the idea is to take a teacher network that's much larger and use the output from that network to help train a smaller student network to produce similar outputs. And this is something that I think people became more familiar with recently, because allegedly DeepSeek used their smaller model as a student and used maybe an OpenAI model as the teacher to great success. And then something that is near and dear to my heart, because I'm applying pruning methods right now in my work, is pruning. And so the idea here is to take the lower magnitude weights and either zero them out or even just remove them completely from the model. And there's structured and unstructured techniques. With unstructured, you allow yourself to kind of remove them without any imposed constraint on the structure that you're moving. So you could imagine having like a weight matrix and being able to remove a weight at an arbitrary location. But one challenge when you're trying to deploy to the hardware is that you need some mechanism to keep track of all of the remaining non-zero weights. And that's something that's right now more challenging to do given the hardware constraints that we are working with. So I've been working with structured pruning, where you're removing entire rows or columns of weight matrices or channels. And then in the end, you fine tune to restore the performance and have a smaller model to deploy. But I think something I want everyone to take away is that this is a very iterative process, as Yuval mentioned. Sometimes we're trying like one or more of these methods at once, and it results in a lot of different versions and experiments. And we really want to have a good way to keep track of our learnings and the different experiments that were done. And that's kind of where weights and biases has come in. So I stole this screenshot of a model tracking spreadsheet that a team was using on one of the projects that I worked on to illustrate kind of the pain that we had tracking our different versions before we started using weights and biases on some of our projects. And it's very heavily redacted because I'm trying to protect some of the details of this project, but I think you can get the idea. I'll walk you through a little bit. But in this case, for this project, we had like experiment names. So we're going through trying to make this model smaller, and each row is a different attempt or kind of candidate model trying to do that. And you can see kind of from the unredacted parts that the names aren't always super informative. So it's hard to go back and be like, what were we trying to learn with this experiment? And also on this project, we were doing training on AWS. So this column shows the location in the S3 bucket where the model directory was. So each directory had a model config file, and we were also saving products of training like checkpoints. And so we were able to reproduce our results, although that doesn't make the spreadsheet much easier to parse like as a person. Something else that's kind of unique about our work is that we're collecting data in parallel to our algorithm development efforts. So we're collecting data, but also like as we're doing the algorithm development work, learning about the physics of the sensor and the problem that we're trying to solve and what the challenges are. And we're using those learnings to kind of inform like what experiments they should be conducting in the lab. So we have data sets that are constantly evolving through our algorithm development process. And that's something that's really hard to capture in a column in a spreadsheet like this, and something we've been able to do more effectively using weights and biases recently. And in this case, I think you've also mentioned we usually start with like an open source model. In this case, it was something from a paper, and we were then iterating on it to try to make it smaller. And you can see our progress as you kind of like move down the column. We're able to make the model smaller. One of those columns is the size of the parameters, and another one is the number of max, which is the multiply and accumulate operations required to run inference in the network. But it's really not enough that we're able to make it smaller. We also need it to perform and hit like the product specs. And so this is only a subset of the spreadsheet, but we're tracking many different metrics, and it's just very hard to look at the spreadsheet and understand what was learned at each stage. And so we're excited to have moved on to tracking experiments using weights and biases. So this is just a screenshot showing that we are doing that on one of our projects, but in the next few slides, I'll give you more detail about how exactly we're doing that and some specific examples. So usually as an algorithm researcher, when I arrive on a project, my colleagues have already figured out how to collect data from our hardware. And then there's a collaborative process where we're trying to figure out like what fields should we have in the data and what experiments should we conduct to enable us to do the algorithm development process. And eventually this evolves into a data pipeline. And that's what I'm showing here on this slide for one of our projects. So starting on the left, it all begins when my colleagues in the lab conduct an experiment and create a new data file. And on this project, that data file would be put into a shared directory. And then we used Apache Airflow to automate the process of detecting that there's a new file present. And it also launches a routine that extracts metadata from the file. And we store that metadata as an artifact in weights and biases. And you can see a screenshot there in the middle. But for us, because we have this evolving data set, it's very important to kind of have data awareness. We want to make sure our algorithms can work across all the different conditions that we may see in the real world. And so given that we kind of have the metadata stored in weights and biases, we can then use these like very helpful visualizations to understand kind of the state of our data set. So on the upper right here, for this particular project, we had an interest in making sure that the algorithm could perform at all different temperatures that you see here. And so you can see how much data we had for each condition. And then the colors are showing us how much data we have for another condition of interest, like in the real world. So having this data awareness is something that we found very helpful in our work. So yeah, oftentimes we're kind of balancing the size of the model with its performance. And ideally, we'll be able to find a solution that is both small enough for the embedded hardware and can meet our performance specs. And so what I'm showing here is how on one of our projects, we used weights and biases sweeps to kind of probe how sensitive the model performance is to changing some of the different parameters that are associated with its size. And I love a fancy algorithm as much as the next person, but oftentimes for us, the simplest solution that can get us the performance that we need is what we want to go with. And in this case, it was actually a regression algorithm, believe it or not. And so that was great that it could be that simple. But you can see in this sweep, we're varying across the sweeps the regularization parameter. We're varying a parameter associated with the size of the regression model. And then we're also kind of tracking different performance metrics across the different sweeps. In one anecdote, we really appreciated like the fault tolerance of the sweep feature. We had an incident where a colleague, unbeknownst to us, migrated our weights and biases instance from one server to another during a very large sweep experiment, and it actually kept its state, and the experiment kind of continued with limited interruption. Another thing we appreciated is like you can see the sweep results as you're running the experiment and add additional conditions, and we're trying to do our work fast to create products, and this helps us iterate more quickly. So this is a plot that was created in WAN-V based on the experiment from the last slide, and I'm someone that just loves like insightful plots that contain like easy to access information, and so I think this plot is really great. So just to help you understand what you're looking at, each curve represents a different sweep. And then in our case, we wanted to track the RMSE error of this particular algorithm. And so the color bar is showing that RMSE error. And time. Just wrap up. Okay, cool. Yep. So, and that concludes our talk. Yeah. Yeah.